Welcome to the lectures on modern digital communication techniques. In the previous lecture, we have discussed about the Kraft inequality, and in that particular discussion we said that given a number of code word lengths, we have to find out whether using those lengths one can make a prefix free code. And before that particular lecture, we have discussed why do we need prefix free code, and that issue came up because we are talking about unique decodability, and we took up unique decodability because we had taken up variable length code, and we had taken up variable length code because we saw that if one would take the advantage of the probabilistic nature of the source, then instead of going for a fixed length coding, if one goes for variable length coding, one could save a number of bits per source symbol, and that would effectively reduce the number of bits that gets transmitted. So, that means we started with fixed length coding, we moved on to variable length coding. After studying variable length coding, we found we required the condition of unique decodability. When we studied unique decodability, we defined it, we found that we would require prefix free code so that we could instantaneously decode the received bits. Once we studied prefix free codes, then we set forth to study that given a set of lengths, whether these lengths would satisfy a certain condition known as the Kraft inequality, so that we can be assured that whether a prefix free code can be constructed out of these lengths. Once you are sure that one can construct a prefix free code, then one could go ahead and build the binary tree as we have discussed, and take each of the leaf nodes as the code words, and starting from the root going through the branches through the nodes onto the leaf, one would select the string, the binary string, as the code word. We also said that any intermediary node would serve as a prefix, and since intermediary nodes are not code words, all the code words produced out of this method are prefix free. And then we said that well, these conditions are fine, and we further defined something known as a full tree and a not a full tree. By full tree, what we meant is that the tree cannot be shortened without destroying the prefix free property, and no code word can be added without destroying the prefix free property. So, with this we moved on further and tried to find out that is there a number known as the minimum number of bits per source symbol, and we denoted it as the L bar mean, where L bar was the average number of bits required per source symbol. This average number of bits required per source symbol is used because we are taking variable length coding. So, once you have variable length coding, each code word would be of different length or could be same length, but overall there would be various code word lengths. Of course, one can argue that one particular case can be constructed out of this code tree where all the code word lengths are same, and what we will find is that that is a special case, and the results would be obvious very soon. So, when we were discussing these things, we looked at the Kraft inequality, and the condition that we had was sum of 2 to the power of minus L j, j equals 1 to m, m is the number of symbols in the alphabet, should be less than or equal to 1. So, with this condition, we found that these lengths which satisfy this condition could create a prefix free code, and when this holds with equality, that means if this is equal to 1, in that case we found that a full tree can be constructed. Then we moved ahead and we wanted to find L bar. L bar is basically the expected or expectation of L of x, and where we reached is that L bar could be written as sum over p j L j, where p j is the probability of the jth symbol and L j is the length of the jth code word. So, we wanted to find the L bar min as a minimum value of L bar subject to Kraft inequality condition. So, we wanted to find all the set of code word lengths that would minimize the expected length subject to this Kraft inequality. Now, why we have Kraft inequality? The reason is we wanted to find the minimum length over all prefix free codes. Now, prefix free codes, the reasons we have already explained, and we set up the mathematical problem in the lecture as this, that L bar min is equal to the minimum of this summation, which we have just defined, over all possible lengths subject to Kraft inequality, as we have written over here. And while proceeding with this, we said that this minimization is achieved when we rather have this condition being equal to 1, because if this is not equal to 1, that means one of the code word lengths could be shortened. An example was taken over here, that this particular code word length could be shortened. So, if this could be shortened, then it becomes a full tree. In case of a full tree, this condition is valid, and therefore, our condition could be reconstructed instead of this using this. And this particular problem, as we see, we are talking about lengths in terms of number of bits, and obviously this number is an integer number. So, if it is an integer problem, it is not possible to solve it using standard methods. You have to search over and to find the numbers. So, one easier way could be to relax this particular constraint and say that let us have real lengths, and once we find real lengths, then from that we can go to the nearest integer as our solution, or those special cases where these lengths would be integer, that would be the solution for the minimum. And one could also say that for real lengths, one should have this condition, that means the lengths that we find along with the probabilities should be less than or equal to the case than when these lengths are integer. So, that means this particular solution would give a lower bound on the integer problem. So, proceeding with this, with that particular relaxation, we said that one could proceed with the Lagrangian method and well established method. So, there we take the cost function, which is the cost function over here, j equals 1 to m, and we add this Lagrangian multiplier to this constraint, and we have this Lagrangian expression. We take the derivative with respect to Lj, because Lj is what we are trying to find, the set of Lj's which would minimize this. It is minimized over the choice of Lj's, set this equal to 0. This is what we had discussed in the last lecture. So, we move on from this particular point and we see how do we proceed. So, what we have with us is sum over Pj Lj plus lambda times sum over 2 to the power of minus Lj. Since we said that minimization happens when there is equality constraint, otherwise it is the case where it is not the minimum, because it is not a full tree. So, if it is a full tree, it has to be the equality constraint. So, we use the equality constraint and we have this expression. So, when you take the derivative with respect to Lj, you are going to get Pj, we are taking for every j equals 1 to m plus lambda, and here we have to take the derivative of this. So, just a reminder that what we need is basically the derivative of a to the power of bx is what we have. So, although we can use the formula straight away, which is well known, but still like to revise a little bit. So, what we can do is we can say that y equals to a to the power of bx, and we want to take the derivative of y with respect to x. That is what we want to find. So, one simple way would be to take the ln of this, and that would lead to ln of a to the power of bx, which would be bx times ln a, and if you take the derivative on both the sides, you can get dy upon y, because this is 1 by y, and this would be b times ln a and d of x. So, what we want is d of y by d of x, and this would be b times ln a times y. So, b in our case is minus 1 and a in our case is 2. So, what we have is minus ln of 2 times 2 to the power of minus x, right. So, when we translate that over here, what we get is a minus ln of 2 times 2 to the power of minus Lj. Look at this. this is the same, and of course, this term is 0, and we set this equal to 0 as per our previous step. Take this derivative and set it equals to 0. So, we have taken the derivative and now we have set this equal to 0, and of course, this is true for all j in the range of 1 to m. So, this would give you that 2 to the power of minus L j is equal to P j. We take this on the left, or we take P j on the left, take away the minus sign, P j upon lambda ln of 2. Because of this minus, it is a plus on both the sides. Now, since we know that, or simply we can take the summation of j equals to 1 to m on both the sides, on the left hand side and right hand side. So, 2 to the power of minus L j is equal to 1 upon lambda ln 2. This is not a function of j, sum over P j. So, this is what we have. Now, sum over P j, since we have taken a full tree, j equals 1 to m, P j should be equal to 1. So, what it means is simply that we are not taking any probabilities which is non-zero, sorry, which is not 0. So, we are only taking probabilities which are not 0, that means lying between 0 and 1, and if there is any symbol which does not occur, it is not in the probability space. It is not part of the source symbol because it is not occurring. So, for it to be a probability space, this summation must be equal to 1. And also what we have is by the Kraft inequality, or the Kraft equality in this case, 2 to the power of minus L j is also equal to 1. So, these two conditions are there with us. Now, since these two conditions are there with us, we use it to get lambda is equal to 1 upon ln of 2. This summation becomes 1, this summation becomes 1. So, this is the result that we get out of this exercise. So, once we have this result, we can use it further, and we will simply bring this back into this equation. So, when we bring it back into this equation, we get lambda equals to 1 upon ln 2, or this cancels out. So, if you look at this, lambda equals to 1 upon ln 2, when you replace it here, this cancels out. So, we can write that 2 to the power of minus L j is equal to P j, right. So, this is what we get, or we can also state that L j, or you can take it as minus L j is equal to log base 2 of P j, or we will simply write log, because whenever we write log in this particular situation, we will be using log base 2, or you could also write L j is equal to log base 2 of 1 upon P j. Now, just to clarify a few things, since P j is less than or equal to 1, so this whole number is less than 0 or equal to 0. So, this is less than or equal to 0. So, that means L j in minus L j is equal to a number which is a negative number, therefore, L j is a positive number. So, at least it clarifies that it is a positive number, and here also we can see that since it is P j is lying between 0 and 1. So, this overall number is a positive number now, this number is greater than 1. So, it is a positive number. So, L j is a positive number. So, this number that we have indicates the length. So, it gives us a relationship between the length of the jth symbol and the probability of the jth symbol. So, all it tells is that for the symbol A j, we have the code which is C of A j, and it also has a length which is L of A j, and it has a probability P of A j. For simplicity, we have written it as L j, and this is P j. So, basically it connects the probability of occurrence of the symbol to the length of code word that one should use in order to minimize the L bar. So, if we have P j, if Pj is equal to 2 to the power of some minus k. In that case, what we have is where k is an integer, is a positive integer. So, is a positive integer. So, Lj is equal to k in that case, right. So, what it means is that when Pj is some 2 to the power of something, in that case this holds with equality and we have the minimization. In other case, it is a lower bound. So, what we have now, we could write that L bar min is equal to minus summation j equals 1 to m Pj times Lj. This we already had. So, what we have is the minimization solution gives us Pj is an inherent property of the source and Lj is what we have found. So, we write it as log base 2 1 by Pj, right. At this point, it is important to note that this quantity on the right hand side, this right hand side quantity, which is the summation of Pj times log of, sorry, this is, if I write log base 2 1 by Pj, it is a plus, this is plus because I have Pj times Lj. So, this is a plus, otherwise if I would bring it on the numerator, or L min bar is equal to summation of Pj times log base 2 of Pj. In this case, I have a minus, which is the same, Pj with a minus. This is denoted as the entropy of the source. This is by definition that this is the entropy of the source alphabet x denoted by x, where these symbols, which contains these symbols, x is equal to a1, a2 up to am. These are the symbols with probabilities Pj. So, in that case, this denotes the entropy, and where the definition of entropy tells that it is the bits, because we have used log base 2, or the minimum number of bits required to represent symbols of the alphabet x. So, this is what we have. So, that means L bar min with the real results, that means not integer lengths, is equal to the entropy. So, that means for prefix free codes. So, if we are having prefix free codes, then h of x, which is the entropy of the source going by this definition, is a lower bound for L bar min. This is a very important result. It is a very important result that we have with us, and we can note that when this particular probabilities are integer lengths of 2, integer powers of 2, in that case we can find these lengths, these lengths which are exact solutions. In that case, this L bar min will attain the entropy. In other cases, when it is not so, we can say that L bar min, in other cases we can say that L bar min is less than or equal to h of x. So, only if it is a integer power of 2, it is equal to the entropy. In other cases, it is lower bounded by the entropy. So, that is a very important result, that if you can calculate the entropy, that will tell you that what is the minimum number of bits that will be required to represent this particular source, and if by providence or if by chance you have the source symbols such that such that the probabilities of this particular source are integer powers of 2, which is not always guaranteed, you can find lengths which would actually meet the entropy of this particular source. Okay. So, with this we would like to move forward, and we would like to go further and discuss about what are the entropy bounds on this L bar mean. That means, we have found one minimum length of it. So, that is the minimum, the lower bound of it, which is the entropy, and which will also show that yes, indeed it is the minimum. We will also show what is the upper bound of this minimum L bar. So, what we are going to look at is the Okay. So, for this we are not going to create anything, any new setup. We will continue with the existing setup that we have. So, for this we say that let x be a discrete random symbol with symbol probabilities P1, P2 up to Pm. In other words, it tells us that we are taking the same alphabet with m symbols, and each of the symbols are having probabilities P1, P2 up to Pm. So, this is all that we have indicated here, and we say that let L bar min be the minimum expected code word length over all prefix free codes for x. Then what we can say is that h of x is less than or equal to L bar min, and it is less than h x plus 1 bit per symbol. So, what it tells us is that the entropy bound on L bar tells us that it is lower bounded by the entropy, and it is upper bounded by at most 1 bit from entropy, that it is not taking more than 1 bit from entropy. Now, this is a very important result which relates the minimum length of the code word over all possible prefix free code word lengths to entropy. So, it also tells, we can also add that further, that L bar min, we have already discussed this, is equal to h of x. We have already explained this, if and only if p of j is an integer power of 2. This we have already discussed in the previous note that we were writing, that, and we have also seen that when because Lj is log base 2 of 1 by Pj. So, if Pj is integer power of 2, because we are taking log base 2, we are going to get this integer number in the length. Okay. So, first we are going to take this part. So, that means we first will show that h of x is less than or equal to L bar. Now, since L bar min is the minimum value of L bar. So, if L bar, or if h x is less than or equal to L bar, then of course, L bar min is the one which is, or h x is less than or equal to L bar min as well. So, what we have is that we will take h of x minus of L bar. So, if we write this, what we have is h of x is denoted as Pj log base 2 of p j with a minus sign, and if you take L bar is minus p j times L j. Now, look at this, H x is defined with respect to this, and when I said L bar, what we mean is that we have these lengths L j and we have these probabilities p j. So, if we have these lengths L j and we have this probabilities p j, then this quantity is the L bar and this quantity is the H x. So, moving on further, what we have is this should be equal to minus summation of p j log base 2 of p j. So, we have not done anything to this quantity, only this quantity we change it slightly, that p j log base 2 to the power of L j. So, effectively this is L j. So, we have not made any changes there. So, we continue further and what we have is sum of p j, that is what we have common in both of them, there is a negative sign, log of course p j upon 2 to the power of L j, right, is log base 2, or you can reverse it, bring the negative sign inside. So, what you have is p j log of 2 to the power of L j upon p j. At this point one has to use important result which says that ln of u is less than or equal to u minus 1. Now, this can be graphically understood also. At this point we will not go into that, we will rather remain over here, ln is equal to this. So, you could write ln of u is less than or equal to log base 2 of e times log base 2 of u is less than or equal to log e base 2 u minus 1, and this equality holds only at the value of u equals to 1, because equality for u equals to 1. So, when u is equal to 1, you can clearly see the right hand side is 0 and definitely the left hand side is also equal to 0. So, if we use this, what we get is this particular side, what we have is this whole thing is less than or equal to, because we have a log base 2. So, we are using that. So, log base 2 of e and summation, we have p j as p j, and this one is what we are going to replace, 2 to the power of L j upon p j minus 1. So, now when we take p j inside the bracket, what we have is log base 2 of e multiplied by sum of 2 to the power of L j. Let me see if we have done it right. What we have is we have made a slight mistake at this point. We could have actually taken this as plus and we could have taken this as minus, and then our expression, because this is a minus. So, we have a plus, we have a minus over here. So, this equates out, and what we have over here is this is not of our interest. So, what we have is this one, p j log base 2 to the power of minus L j by p j. So, we have this p j cancels out, minus summation of p j is basically 1, and this quantity is less than or equal to 1. So, what we have in other words, that this quantity is on the right hand side is less than or equal to 0, or in other words, what we started off with h x, at this point we can write h x is less than or equal to L bar. So, this is the first part of the proof that we have established, and in the next lecture we will establish the next part of the inequality, which is an upper bound on L bar. Thank you.